Okay, so you should have a basic idea of about what a limit is, and now we're going to learn some techniques for evaluating limits analytically. And we've got three really helpful rules here. First of all, the limit of a constant b as x approaches c is always b. And that's because when you think about it, if y equals b, it doesn't matter where c is. As x approaches c, you are always going to be approaching b for your limit. Okay, the second one is the limit of x as x approaches c is c. Well, if we graph the line y equals x, then every point on that line has the same x and y coordinate. So as x approaches c, y also approaches c. And then finally, the limit of x to the nth power as x approaches c is just c to the nth power. In other words, you can just plug in whatever c is for x and you'll get what the limit is. Okay? So that means that we can evaluate any polynomial simply by replacing every x with the value that x is approaching. And we can evaluate any rational function simply by replacing x with the value that x is approaching, c, provided that if we plug in c into the denominator, it does not make the denominator 0. So that's really important to watch out for. Okay? Make sure your denominator does not go to 0 as x goes to c. So let's look at some examples. Well, this is a polynomial, so we are safe to just plug 2 directly in. So the limit of this polynomial as x approaches 2 is 2 cubed minus 3 times 2 plus 1, which is 8, minus 6 plus 1, which is 3. Okay, how about this rational function here? Well, when I plug in negative 1 for x, that will not make my denominator 0, so we're safe plugging it in. So I get negative 1 squared plus 2 times negative 1 minus 4 all over negative 1 minus 2. That's going to give me 1 minus 2 minus 4 over negative 3, and that'll give me negative 5 over negative 3, which is 5/3. So that is the limit of this rational function as x approaches negative 1. Well, what about radicals? Well, you can plug c directly in for x if the index of your radical is odd and if it makes the radicand greater than 0 when your index is even. So, for example, the limit of the square root of 4 minus x as x approaches negative 2 will be the square root of 4 minus negative 2. Now this is an even root, but when we plug in negative 2, the radicand becomes positive, and so my answer is the square root of 6. Okay, over here, I'm going to do the cube root of 2 minus x as x approaches 3. So it's going to be 2 minus 3, which is negative, but we're safe because our index is odd. So this becomes the cube root of negative 1, which is negative 1. Okay, now what happens when you plug in your c value for x and you get some weird stuff? For example, if I plug in c for x, if I plug in 2 for x right here, I'm going to get 4 plus 6 minus 10 all over 2 minus 2, which is 0 minus 0. Well, that's something that we can't deal with, right? That is called an indeterminate form. And so we have a couple of strategies that we can use to get around that, and hopefully you will be able to factor and convert this rational function that is indeterminate into a function that is no longer determinate. And you'll notice that I can factor the top into x plus 5 times x minus 2 all over x minus 2, and now I can cancel those x minus 2's, and it is safe to plug in 2 for x, and I get 7. Now remember that the value of the function doesn't have to exist at 2. We just have to be able to approach this for the limit to exist. Okay, how about this one? If I plug in 0, I'm going to get the square root of 6 minus the square root of 6 over 0, which is 0 over 0. Once again, that's indeterminate. We don't like that. So here's what you do when you have a couple of radicals being subtracted. We're going to multiply the top and bottom by the conjugate of that numerator. So the conjugate of the square root of x plus 6 minus the square root of 6 is going to be the square root of x plus 6 plus the square root of 6. And that's really just 1, so we're safe doing that multiplication. Now on top, I have the difference of two squares, so that is x plus 6 minus 6. And on the bottom, I have x times this whole thing right here, this conjugate. And so on top, the 6's cancel. I have x. I think y'all can see where I'm going with this. Now I can cancel that x, and I'm going to take the limit as x approaches 0 of 1 over the square root of x plus 6 plus the square root of 6. And that's perfectly safe to plug in 0 for x now. We're going to get 1 over the square root of 6 plus the square root of 6, which is 1 over 2 root 6. So that's our answer. Okay, now I need to talk about this squeeze theorem here. And what it says is, if I've got three functions, and h of x is always less than or equal to f of x, and both of those are always less than g of x, then the limit of h of x, if the limit of h of x equals L, which also equals the limit of g of x, then the limit of f of x exists and is equal to L. Alright, that sounds kind of confusing, but here's what's going on. Let's say that h of x is doing this. Okay, and here is c. So the limit of h of x as x approaches c equals L. So there's L. And let's say that f of x is between h of x and g of x. So I'm going to put g of x like this because its limit as x approaches c is also L. So there's g. And f is between them. So f is, let's say, doing something like this. Okay. So if that's the case, where f is always between g of x and h of x, and the limit of g is equal to the limit of h as x approaches c, and that's equal to L, then guess what? The limit of f is also equal to L. In other words, f is squeezed into the same limit that h and g are equal to. Now we use that squeeze theorem to figure out two trig limits that you need to memorize because they're going to come in very useful later on. The limit of sine x over x as x approaches 0 is 1, and the limit of 1 minus cosine x over x as x approaches 0 is 0. And how do you use these? Well, this is very similar to this one up here, and we can use this one as long as the coefficient of x up here is equal to the coefficient of x down there. So I need to make this 3x. Well, that's not hard to do. All I need to do is multiply the top and bottom by 3. And then this 3 now can move around to the front of the limit. And this whole limit is equal to 1. And so our answer is 3.